All right, so let's do our first example. Let's look at what happens when we look at the loads just to the left and actually just under P, right? Not so much to the right of it, but and at P actually. And in order to do that, the first thing we'll do is actually bring in more knowns, right? So we'll look at calculating the support reactions by drawing a free body diagram of the whole thing. And this should be something we're all pretty good at now. So I'm going to let you pause and do that. And then come back and tell me what you can check with what I have next in terms of what the support loads are. So here's my free body diagram for the support reactions. Of course, at the roller we have just an AY force, and at the support B we have a pin, BX and BY. We can see by inspection that there are no other forces in the horizontal direction, and so therefore that's why BX automatically goes to 0. And if we take the sum of moments at A and then combine that with sum of forces at Y, you should get that BY equals 1 kilonewtons and AY is equal to 5 kilonewtons. So now we can start actually separating. And first, our next step now is to create, since we want to know what's happening to the left and at P, we'll go ahead and create an imaginary section through the member. So that's what I've done here by drawing just a little imaginary cut, just like method of sections. And then what will we do? Next is draw a free body diagram of those members and identify the one with the least number of loads so we can understand what's happening. We're actually going to go ahead and go through both. But let's go ahead and set up those free body diagrams first. So we'll take the left-hand side first, draw a coordinate system, and where that section is, so, sorry, here, we'll still apply AY. We're going to be just to the left, right, for right now, the left-hand side. And using our positive force sign convention for internal forces, we'll draw a tensile normal force, a shear force that creates like a clockwise rotation, and then a happy moment, a positive concave moment here. And now if we do the right-hand side, what we'll see is we'll still have our external forces, By, the externally applied moment, 9 kilonewton meter. And now we'll go ahead and include that 6 kilonewtons, right? And in terms of the internal loads, a positive normal force that creates tension, a positive shear that generates that sort of clockwise spin, and then a concave moment, M. What you can see on the left is we only have 4 loads essentially acting, and on the right we have 6, right? So let's use the left-hand side first to actually resolve what the internal forces are at that section just before P. And so sum of forces X tell us that N equals 0. Sum of forces Y, we have an AY minus V equals 0. And then if we go ahead and take the sum of moments at that point C, right, here, we'll see that we have minus AY times 3 meters, because this distance here is 3. On the left, it's 6 meters here. So minus AY times 3 meters plus M equals 0. So in terms of the internal loads, we see that there's no normal force. Shear is equal to AY, and the moment is equal to AY times 3 meters. Numerically, this is equal to 5 kilonewtons, and this is equal to 15 kilonewton meter. So that's our solution there. Now what happens if we look at the right-hand side? And so I already have a free body diagram prepared for that. I thought I did. Yep. So let's take a look at what's happening at the right-hand side. I'm just going to scoot this up so we can put these next to each other. And now let's look at those equations here for the right-hand side free body diagram. So again, we'll do sum of forces X, and we see that again N equals 0. Sum of forces Y, we have V positive minus 6 kilonewtons negative plus By positive equals 0. So now V is equal to 6 kilonewtons minus By, shear. And if we again take the sum of moments at C, we see again that By now has a moment arm 6 meters, our applied external moment 9 kilonewton meters. 6 kilonewtons does not contribute to a moment at C, neither does the shear, and of course the normal is 0 anyway. And so all we have left is just M, which is going to be a negative because it's going in the negative, right? It's generating a clockwise M here, which is of course then negative, right? So just keeping track of our signs. And now if I solve for M, I see that M is equal to By times 6 meters plus 9 kilonewton meters. And substituting in, we know that By is equal to 1 from above. So shear is again equal to 5 kilonewtons. And now similarly, this is 1. So now moment is equal to 15 kilonewton meters. And this should hopefully make sense that we would expect that the shear and the moments and the normal forces to all be the same, right at that same point where we've essentially made the cut. And so we do in fact get the same set of forces here, 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 and here, right? Okay, let's do another example.